Okay, so on the last day we discussed 5 problems from the assignment number 1 from electromagnetic theory. The link of the course from which these assignments are taken is given in the first comment. You can check it out, and you can also watch the first video by clicking on the I tip, or you can also get the link in the first comment. So we'll start with problem number 6. So let's read the problem. You can get the PDF of this assignment from our Telegram group. The Telegram group link is given in the first comment. So let's start. Question number 6. A point charge Q sits at the corner of a cube of side A, as shown in the figure on the right. The flux of the electric field vector through the shaded area is. So you are given a cube like this, okay, and it is said that a charge Q is sitting at one of the corners, and you have to find out the electric field through this area. So how can we do this problem? To do this problem, we can utilize Gauss law. According to Gauss law, you know that the total flux coming out of the Gaussian surface is Q enclosed by epsilon naught. But here you see, in this case, the charge Q is not enclosed. Okay, so first we have to enclose this charge. To enclose this charge, what you can do? You can extend this cube, you can extend on this side. 4 cubes will be there, and 4 cubes in the below side. You must have seen the Rubik cube, so you can consider like that. So I am just showing you. You can consider a big cube like this, okay, and let me just draw it for you, or you can also draw it by yourself. It is like this. So we have to divide this big cube as 8 smaller cubes. So you can just join these like this. We are joining. My drawing is not so perfect, but bear with me. I am trying my best. Okay. So it's a mistake I have made. Okay. So in this way, you can see you will be getting 8 cube. Okay. If you join these things in this way, you will get around 8 cubes. So your charge is you can consider your charge is sitting at one of the corners. So it is like this. Your charge is sitting somewhere here. So now you can apply the total flux coming out of this big cube is Q by epsilon naught. Now there are total 8 faces. 1, 2, 3, 4, 5, 6. Sorry, 6 faces. So by one big face like this, what is the flux coming out? It is 1/6 of the total flux. Now you can see this is the unit which is given to in the question, and this is the side shaded portion from which you have to calculate the electric flux. And you can see this face, this small face, is 1/4 of this big face. So if you multiply with 1/4, you should get Q by 24 epsilon naught, and that is the amount of flux coming out of this shaded area, and it is matching with option C. Okay, so you can do this in this problem. A similar problem is given in question number 7. Sorry, what's happening? Okay, so a charge Q is at the base of a cone of height h and base radius a. Okay, so this is the cone. Let's say it has base height h, base radius is a, and the charge is sitting here. So you can utilize a similar logic. This charge must be enclosed. If you want to apply Gauss law, this charge must be enclosed. So how can you enclose? You can just extend this flux in the lower portion in a similar manner in this way. So from this total cone, upper and lower, what is the total flux coming out? It is nothing but Q by epsilon naught. Now we have been asked to calculate the electric field of flux of the electric field through the curved surface. So you see there are two curved surfaces and this is the total flux coming out. So through one surface, what will be the value? Half of it. So Q by 2 epsilon naught. It is matching with option B. So option B is the correct option for this question. Let's move to question number 8. What does it say? Let the electric field in some region is given by E is equals to e to the power minus e square I cap plus e to the power minus x square j cap. From this we may conclude that, what conclusion we can draw from this? So four statements are given. R has a non-uniform charge distribution, R has charge distribution, R has no charge distribution, R has a time independent magnetic field, and the energy flux in R is 0 everywhere. So for this electric field, you can see if we calculate, let's say, divergence of E. If you calculate divergence of E, what value will you get? If you calculate it, you will get it 0. So divergence of E is equals to 0, and from differential form of Gauss law, what do you know? Differential form of Gauss law gives you divergence of E is equals to rho upon epsilon naught. So if this divergence of E is equals to 0, that directly corresponds to rho is equals to 0. Rho equals to 0, rho is the charge density, volume charge density, rho is equals to 0 means there is no charge distribution. So from this logic you can getting option B correct, and further you can cross check for the other options, like if you find out curl of E, you will find out to be not equals to 0, and curl of E equals to minus del B del T. Del B del T means dB dt you can consider. This is also not equals to 0 means B is time dependent, but in option C, R has a time independent magnetic field. That is incorrect. So option B is correct for this question. So option B is the correct option for question number 8. So question number 8 is also done. Let's move to question number 9. Question number 9, let's read the question. Question number 9. What does it say? A charge q is moving with uniform speed, enters a cylindrical region in free space at t is equals to 0 and exit the region at t equals to tau. Which one of the following option best describes the time dependence of the total electric field phi t through the entire surface of the cylinder? So the cylinder is given like this, and a charge is entering into the cylindrical region at some time t is equals to 0. So you should keep in mind that the electric field exists only at this cylindrical region, and your charge q is coming in this path and it is entering. So let's say it is entering at t is equals to 0 at this point, and it is going through this cylindrical path and leaving the cylindrical region, means it is leaving the electric field region at t is equals to tau. So you have to find out, you have to plot like how does the flux phi of t versus t looks like. Let's say this is t is equals to 0. Now we can utilize here also Gauss law. According to Gauss law, the flux phi is equals to q enclosed by epsilon naught. This is the thing you have to keep in mind. Now it's a beyond t is equals to 0, there is no flux coming out. Okay, when it is entering the cylindrical region at t equals to 0, the total charge enclosed is q enclosed by epsilon naught. So some value like this is q enclosed by epsilon naught, so this is q by epsilon naught. Fine. Now let's say the charge is coming here, so it is moving from here, but here also the total charge enclosed is q, so it will maintain the value. Here also total charge enclosed is q, here also total charge enclosed is q, up to t is equals to tau. The total charge enclosed will be q. Okay, and once it is leaving this cylindrical region, the total charge enclosed becomes 0, because the electric field is only existing at this cylindrical region. So beyond t equals to tau, the flux coming out of it will be 0. So this will be the presentation of phi t versus t, and you can see it is matching with option D. Option D is the correct option for this question. Let's move to the last question of this assignment, question number 10. Just rubbing it out. what does the question number 10 say? Question number 10 say, okay, a static charge distribution gives rise to an electric field of the form E is equals to, so the electric field expression is given to you, alpha times 1 minus e to the power minus r by capital R cap upon r square. Alpha r positive constant, the charge content within a sphere of radius r centered at the origin. This question is very simple. You know from Gauss law, Q enclosed is equals to, it will be epsilon naught. Basically E dot ds is equals to Q enclosed by epsilon naught. So Q enclosed is equals to epsilon naught integration E dot dA or E dot ds, you can write. Now this is given in spherical polar coordinate, so you can write your vector dA. dA is equals to r sin theta d theta d phi, and the direction will be r cap. So if you replace this and if you take the integration, you will get a general expression of Q enclosed. And finally you have to find out the charge content within a sphere of radius r. And after evaluating the general expression for Q enclosed, if we put, so Q enclosed will come in terms of the small r. Now if you put small r is equals to capital R, then whatever value you will get, that will be your answer. Simple. You can easily evaluate this integral, and you will find out option D to be the correct option. So I hope you have understood all the solutions. I have tried to explain as much as possible. If you need any solution in more detail, you can let me know in the comment section. I will definitely try to make a dedicated video for that particular problem. And if you are new to this channel, please subscribe to the channel and don't forget to press the bell icon. Finally, thanks for watching. Unacademy is India's largest online teaching learning platform. You can prepare for various competitive exams like CSIR-NET, GATE, JEST, IIT-JAM, TFR. Especially if you are preparing for CSIR-NET Physical Science, you can join me on Unacademy Plus. I cover all the 9 units of CSIR-NET Physical Science syllabus. My approach is especially I precisely give you the concept of the concerned topic. Then I discuss the relevant mathematical formula and do the analysis. Relevant problem based on the topic, including previous year questions, are discussed. Homework and assignments are also given. This is my profile, and if you want to join my Unacademy Plus courses, you can enroll for this course. And if you are new to this Unacademy platform, you can take an Unacademy Plus subscription using our referral code FELIXHUB, and Unacademy will give you 10% off. So take the Unacademy Plus subscription today and put your feet one step ahead towards reaching your goal. Thank you.